start by, I just want to really quickly go through a couple of the key take-homes of the work that we did in class on Tuesday, right? So, and actually by extension Monday. So basically what happened on Monday and Tuesday was we were really focused on just finding momentum. That was the big thing. And momentum is easy to calculate, simple multiplication, mass times velocity. But where things get a little tricky is that when you have multiple objects and you're looking at their momentum at multiple times, then it's a record-keeping nightmare. Somehow you have to know which of your velocities is the velocity of the first car before the collision, which is the second car before the collision, which is the first car after, which is the second car after. You generally are going to have masses that stay the same, but that's not always a given. You're going to have momentum before the collision of each cart. You're going to have momentum after the collision of each cart. You're going to have combined momentums. Then there's all sorts of other things that we can do, like we can find how one cart's momentum changed from before to after the collision. And let's not forget that we're not always going to be talking about carts, and we're not always going to be talking about two objects. So things like expand exponentially in terms of the record-keeping complexity. The basic idea is always going to be relatively simple, mass times velocity. In the virtual collisions lab analysis, there are a couple things that I really wanted you all to see that you can't because my screen is frozen. The first thing that I wanted you to think about was this piece right here. Does it appear that there are significant forces acting in the direction of motion of the objects besides collisions between the objects? How do you know? That's a weird question because it sort of gets at the idea that maybe I should have told you something. But there's a couple things. One is I did really super briefly mention it on Tuesday. Didn't expect any of you to notice it. In fact, I told you, you don't even need to write this down. I said, we're hinting at this down the road. So I told you kind of why this is important. But the cooler thing about it is you already know everything you need to know to answer this question. It's a different context. So some of you, it didn't occur to you, but here's what I want you to recognize. If we are looking at one axis of motion, so if we've got a collision between these two objects that is one-dimensional, and this one was because the two, well, I guess they were balls, right? So we had these two balls moving toward each other. They collided. Their motion was either in one direction or the other direction. There possibly, we don't know how this simulation was built, there possibly were forces at right angles to the motion of these objects and the collision. We don't know anything about them except whatever those forces are, they must balance because we didn't see any acceleration of either object in this perpendicular dimension. So then, the only question is, so we can just, maybe there are forces, maybe there aren't, it doesn't matter. We don't know anything about them, but we can safely ignore them because we know they sum to zero the entire time the simulation is running. The second question is, what about forces in this direction? And some of you are like, well, yeah, there's a significant force when they bonk into each other, but what the question is asking, oh, I see why that's not working, that's funny. What the question is asking is, are there significant forces besides the collision itself? When they hit each other, there are forces. Before they hit each other, are there any certain forces of significance acting on these objects? And after they hit each other, are there any forces of significance acting on these objects? Here's how you can answer that question. Look at the motion of the objects before and after the collision. And what you'll find is that in this simulation, the velocity of each object will stay the same. And then they hit each other, there's a change at that moment, and then after the collision, the velocities stay the same again. We have constant velocity before, constant velocity afterward. That means acceleration is zero. That means the sum of the forces in that parallel dimension, which we could call the x dimension, is 0. Could there be forces acting on these objects? Yeah, there could be, but they're not significant, and the reason is because they sum to 0. So if there's other forces acting on these objects besides the collision, they're not affecting the motion of the object. And that ends up being really important, because when we start investigating conservation of momentum, which we're going to look at just a tiny bit right now, but mostly is going to be our topic for next week. When we start looking at conservation of momentum, what we'll see is momentum in a system is conserved only when this is true. When acceleration is 0, velocities are relatively constant before and after the collision, which means the only thing that affects the motion of the objects is the collision itself. And in that case, we can make some interesting predictions about what's going on. So that was the first thing I wanted you to get from the virtual collisions lab analysis. The second thing that I wanted you to see is just like what we can do with some of these numbers. Okay, so I went through this with all of you. I did an example and I showed you how I use spreadsheets to keep track of this stuff. There are going to be times when I require you to use a spreadsheet. This isn't one of them, but one of the things that's nice about this is when you try to set up a data table like this on paper, things can get muddled a lot more easily. Like you run out of room or you can't read your handwriting. So one of the nice things about this is there's some clarity to what's going on. If I decide it's easier to have the velocity of ball 1 and then the velocity of ball 2 before the collision here, and the velocity of ball 2 or ball 1 and ball 2 after the collision here, I can do that. I can just like move these columns around. I'm not going to now, but it's kind of nice to be able to reorganize the data if you need to. The other thing that's nice about this is, and this isn't a requirement, but super helpful, if you teach yourself a little bit about how to use equations and formulas in sheets, then you can have it do the math for you. So over here, where I'm finding the momentum of ball 1 before the collision, I just knew that it was 1 every time because its mass stays the same, its velocity stays the same. It's always 1. But the velocity of ball 2 changed. I did that calculation on with my calculator while you were watching, and then the momentum of ball 2, same. Momentum of ball 2 after the collision, same. And then I did something a little bit different, which is, this is interesting. This isn't what I did. Hang on. Oh no, I wanna, okay. All right, you'll see all this anyway. So this has been altered, and it's okay. So what I did is I used equations. I used equations for all of this stuff, because that makes it a ton easier to do the math. So I'll show you how that works right now. Before I do that, I want to show you a couple of things that you should have noticed from the lab. The first is, if you did most of the record keeping and calculations right, then you would have seen that most of the time, your momentum, total momentum before and after the collision was very close. These minor differences are rounding errors. We're going to see minor differences as well. When we do real calculations with momentum, it won't be rounding error though. It'll be measurement error. There's no measurement error in this simulation because it's designed to be perfectly theoretically accurate. Everything is calculated out to the nth decimal, and everything is accurate. If it tells you that the velocity is 0.475612222, then it is exactly that. In real life, when we measure stuff, we're like maybe within 1 or 2% at the best. And more often, we're looking at somewhere between 10 to 20% measurement error. So if you measure your car's velocity and it's 1 meter per second, then maybe it's 1, maybe it's 1.1, maybe it's 0.9, maybe it's 1.15. Like, we don't really know, and we never really will. But here, any differences you see between these numbers are purely due to rounding error, which means effectively the momenta before and after the collision for all of these trials should have been the same. Many of you will have seen that that's not how it played out, that you got some significant differences. That's because you messed up. You wrote down a number wrong, you used the wrong number in an equation, you forgot to put a negative sign in, something. They should all match, okay? And that's ultimately going to be more meaningful when we talk about the law of conservation of momentum, how we can use it to make predictions. In this case, this follows from our observation that there aren't significant forces acting on these objects other than the collision itself. When that's true, we can expect momentum to be the same both before and after the collision. And then I asked you to find the change in momentum of each object. And I showed you this, but I just want to remind you that there is a defined equation for the change in something. If I want to know the change in any value, like Q, then I take its most recent value and subtract its initial value. And there might be a sign associated with that. If the thing increased in the positive direction, whatever quantity we're looking at, then the change will be positive. If it became more negative, then the change will be negative. So if I start with $10 and I end up with 14, the change in amount of money I have is +4. If I start with $10 and I end up with 2, the change in my money is -8. Final minus initial. And that's important because when you do the math on these calculations, so I'll show you how to do an equation right now. What I want to do is I want to find the change in momentum for ball 1. That's going to be its momentum after the collision minus its momentum before the collision. I don't have to use a calculator. I'm going to make Sheets do that for me. I'm going to hit an equals sign. That tells Sheets, do some math. And then I'm going to click on my after, type a minus sign, click on before. There's the change in momentum. -1.44. Ball number 1 ended up with 1.44 more kilogram meters per second of momentum in this direction than it started with. Whatever it started with, it ended this much more negative than that in terms of its momentum. And we can do a similar calculation for ball 2. The final momentum of ball 2 is 0.475. I click on that, minus the initial momentum of -0.525, and I get about 1, and that's not right, because that's let's see, ball 2 after. I didn't do that right, hang on. Equals, see this isn't, this isn't my stuff here, hang on. These numbers aren't right. I don't know exactly what happened here. I don't know if it was Sheets or somebody did something, but this isn't the momentum of ball 2 here. So let me do this again. The momentum of ball 2 is its mass times its velocity after the collision. Okay. That looks better. Okay, and now I can take this calculation and this calculation and just pull on that little dot in the lower right-hand corner. And when I pull them down, what I get is Sheets is smart enough to know, oh, well, you don't want to just see that -1.4 again. You did an equation here using this number and this number. And when I go down to this, I'm going to use that same equation, only I'm going to use it for this number and this number. And this is going to reflect this minus this. This will be this minus this. Same for ball 2. So what do we see? What's the pattern that we see? Well, again, there's rounding error. But if we look at these numbers, what we'll see is they're not the same. They're dramatically different, but they have almost the exact same magnitude. They're equal and opposite. So the momentum before the collision and the momentum after the collision were pretty close. The change in momentum of one ball and the change in momentum of the other ball were almost exactly equal and opposite. So that's another kind of observation that we can think about. However much this one changed by the exact opposite amount. And then we can do some more like simple math. We can add these two changes in momentum together. So I'll use sheets to do that. If I add this and this, I get a very small number. If I look at all of those very small numbers, they're just like small, 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 small. Basically what it's saying is the change in ball 1 plus the change in ball 2 is almost 0. And I can do a similar calculation to find the overall change in momentum, change after minus the change before. And what I'm going to find is, where's my momentum? That minus that. What I'm going to find is that these numbers pretty much are all the same. This one right here, there's something is going on with the calculations that isn't right. These numbers aren't what I originally put in, but the rest of these are really close. And this, I could figure this out, right? Like, one of these numbers isn't right, and I could figure it out pretty easily. It's this right here. I can tell right off the bat. One of these is wrong. These two balls have the same speed after the collision of negative 0.02. They have different masses. They should have different momentum. I don't know which one is right. There it is. That was the one that was wrong. So now our numbers match exactly. The change in momentum of each ball added together is equal to the overall difference in momentum before and after the collision. Playing around with these numbers, we're going to start to see patterns over and over and over again. And those patterns are what I want you to see from the virtual collisions lab and the analysis. So here's your job, and this is where, like, we're done talking about this as a class. If you deeply understand everything that I just said, then rock on. Like, if everything I said, if you saw the same things that I did about what happened with these numbers, like something goofy happened, there was some copying and pasting that went on here, and I don't know exactly what happened, but we figured it out. I figured it out just by looking. Some of these numbers aren't right. I was able to fix it. If that's where you are, then you're in fantastic shape. If not, then do not wait to find out later how it's going to affect your understanding. Take some time this weekend, and you've got everything you need at home. This video will be posted. There's other videos posted. Like, take a breath, spend some time at home this weekend looking at this stuff. This is the level with which you need to be able to work with momentum. This is just the mathematical part. We're not really diving into the conceptual part here. Mathematically, if you can't keep track of these kinds of numbers, you're going to be progressively more and more lost as we go. Okay. All right. So that's part one of our work today. Part two of our work today is we're going to start thinking about the conceptual piece. And the activity that I have here is called estimating and finding momentum. And I'm going to go through a couple of things right now that I want you to write down, and I want you to really like internalize, because the point of this work is it's a little tricky. It's really hard for me to explain it in a document. So if you just look at the document and you follow the steps in the document, you're going to get a bunch of information written down, and you might miss the point. Okay, so here are the things that I really want you to be able to do. This is really where we're going with this activity today. The first thing is I want you to be able to roll a supercard with a certain velocity. And what I mean by that is, okay, I know that you're all capable of rolling a cart. You're all capable now of measuring the velocity. But what if I told you roll it at 1 meter per second? Could you do that? Could you do it consistently? So this is a practice skill. I want you to actually like practice rolling things until you can get them to go at a certain speed. That is, it's not something that is super important for fit, like, it's not a skill that everybody needs outside of this class, but as it turns out, the work you do in here is gonna make so much more sense and be so much easier if you can get within at least like 10%. So I'll show you how you can do that. And then the next piece that I want you to be able to do is understand what momentum feels like. We talked on Tuesday about the idea that momentum measures how hard something is to stop. When you think about that, most of us tend to kind of fall into like, well, I mean, that's about force, right? Or something about like how hard it is to get something to move. And the thing is, force and how hard something is to stop are not the same. They're related, but they're not the same thing. They're not the same thing. They're related, but not the same thing. How hard it is to move something and how hard it is to stop are related, but they're not the same thing. So what I want you to do today is get some practice actually feeling what it's like when you try to stop a moving object. You feel the difference, and that is going to be what tells you about momentum. Okay? So these are the two big things. Everything else you do today is gonna be relatively straightforward, but this part is a little tricky. The activity itself, so there's, those two things are the big things, which means however you go about it is fine with me. The way I've put the activity together is it's designed in such a way that if you are really careful with how you do it, you'll achieve those things. So, so I'm gonna kind of go through the instructions here just so that you can see where I want you, how I want you to go about it. But if you end up doing it differently, it's not a big deal as long as you stay focused on those two things. Can you roll a cart at a target speed? Have you been able to practice that, you personally? And can you get it rolling at a good speed? And do you understand what momentum feels like? All right. So the way that I have this set up is there's these masses and velocities. The masses I'm calling target masses because if you take an actual supercart, you'll find that its mass is not exactly 0.285. It might be a little bit more, it might be a little bit less. If you put a bar on top of it, you might find that its mass is a little bit different from 0.785. And when you are like adding other stuff like these things, like these 100 gram masses, some of these might not be labeled correctly. So if you put a mass on there and it says 100 grams, but it's only 60, then you're not, like, you wanted it to be 0.785, but it's not. So there's a column here to write your actual mass when you actually measure it. And same with the velocity, as you'll see in just a second. These are, this is what I want you to try to get, but it's gonna be really hard. It's really hard to roll something and be like, that's gonna be 0.5 meters per second. It takes a lot of practice. So your actual velocity is gonna be a little bit different. There's a calculation here, just to find momentum. Momentum is mass times velocity. I know you can all do this. I know you can all do this with the actual mass and the actual velocity. I also know you can do this with theoretical numbers like this. I want you to do that last. Do not do any multiplication. Do not use a calculator. The very first thing I want you to do is I want you to just guess. Which of these do you think has the most momentum? Most of you are so quantitative, you think in terms of math, that you're gonna be like, oh, I know how I can do that. I'm gonna multiply these two numbers together. But that's not what I want. do not want you to do the math. I know you can do that. I know you can multiply these two numbers and figure out which one theoretically will have the most momentum. What I want you to do is guess first. You can do that in two ways. One, you can just like look at these and be like, well, this one is pretty small, I mean light, has not very much mass and is moving fast. This one is more massive and it's moving slow, which matters more, I don't know, like just guess. The other thing you could do to be a little bit more like refined with this is set it up. So if I take this cart here and I put a bar on it, that's 0.785. And if I just kind of roll it with, you know, I don't know how fast that is, but I can estimate, right? Like if I wanted to roll at 0.3 meters per second, that means it's going to go about 30 centimeters, 33 centimeters every second. So that's to about here. So that's like 1, 2. That seems like that's pretty good. And so I could think about like, well, I mean, I could actually set it up, push things around, and watch them move and think, okay, what do I think has more momentum? After you've guessed, that's when you're gonna do the calculations and test some things. Don't just do the calculations. I know you can all do that. I want you to actually think about it. And in particular, what I want you to think about it is in terms of our conceptual definition of momentum, which is how hard it is to stop something. So this very first question on today's assignment is, what could you do to try to determine which objects have the most momentum and which have the least? But here's the piece that you all have to hear, because if you don't hear this, you're not going to do this right. I want you to do it without taking any numerical measurements or making any calculations. This isn't a multiplication problem. This is a feeling problem. How hard is something to stop? You can feel that. If you take your coin, roll it, you can feel how hard it is to stop. If you roll it harder, you'll feel that it's harder to stop. If you make it less massive, you'll feel that it's easier to stop. You can feel momentum. That's what I really want. I want you to practice and think about and guess and test what it feels like so that you start to have an internal understanding of what momentum actually is, which is how hard it is to stop something. We're going to put that together in a couple weeks with how force plays into it. It's not the same thing, but they're related. So I just answered number 1 for you. What is one easy way you could quickly estimate? Put your hand in front of the cart and try to stop it. Okay. The last thing that I want to show you really quickly is how to get the cart moving at the right speed. So the most important thing is it takes practice, and a lot of it. Okay. All right, and all I need is one graph here because all I need to know about in this case is velocity. So my goal is this cart right now is about 0.285 kilograms. So that's this first one. So that means for this particular mass, I need to target a velocity of about 0.5 meters per second. Here's how you do it. First of all, 0.5 is about 50 centimeters. So I'm gonna just I'm gonna start at 110, which is right here, and this is 160. So my muscle memory piece is I'm gonna try to get it from here to here in about a second. Okay, that seems like that was reasonably close. All right, so now I'm gonna click collect, and I'm gonna see how close I get. Okay. All right, how close did I get? Not terrible, okay? You can see here, it's a little bit more than 0.5. This you can't read, but it's 0.58 meters per second. But over time, it actually is slowing down, which makes sense. So by the time it's gone, you know, like half a meter, it's traveling at about a half a meter per second. So that's not too shabby. If I put a block on there, and I want to try to match what the lab is asking for, now I've got about 0.785. I want this to be 0.3. So I'm going to play the same game. I'm going to put it at 130. I'm going to try to get it to 160 in about a second. Oops, that's not enough. Hang on. That just sort of slipped out of my hands. How did I do? Well, that's pretty good right there. That's about 0.33 meters per second. That's your goal. Roll the cart and have it come within 10% or so of the target speed. Everybody needs to practice it because everybody's going to need to do this. So this isn't one of those things where you get into a group and then one of you is the cart roller. Like, everybody needs to practice it. Okay. And that's my stuff for the morning. Does anybody have any questions before you get started? These are your big goals. This is the stuff I want you to keep in mind. I want you to master the art of getting the supercart to move at a certain speed, and I want you to think about what momentum feels like. Different masses, different velocities, how hard is it to stop? Okay, let's see what you can do.